Hi everyone, welcome to Snetly. In today's video, we are going to discuss about real-time open loop speed control of brushless DC motor with our Snetly real-time controller. Here we will implement both module level design as well as we will configure the hardware section with our controller unit. First we will develop the module level design, then we will go with the hardware configuration by connecting the motor feedback as well as digital output to the inverter module. Then we will run the motor in open loop scenario. First we need to connect our digital input. This kind of motor usually run based on the motor feedback. Here in this motor we have all sensor feedback. Totally we have 3 all sensor signal in the motor feedback with a phase shift of 120 degree. Based on this we need to excite our voltage source inverter module semiconductor switcher so that the motor runs with the inverter module. Since this kind of motor is not a self start motor, we require a voltage source inverter module to run the module. Motor feedback, let me take the digital input. Here 4 set of digital input is available. I am going to configure with one of the pin. In digital input, right click the block to view the configuration window. This is the front layout of our real-time controller unit where we will connect our digital input. From the motor we are getting 3 feedback which we are connected in the 5th pin and 3rd pin and 1st pin of hardware unit. Back to schematic. Now we have to view the waveform. Let me take a logic analyzer. Here the 5th pin is our all A signal and 3rd pin will be all B signal and the 1st pin will be all C signal. By clicking on run button while rotating the motor we will get the feedback from motor high and low. So here high means red color will be indicate, low means it will be in green color. Here totally we will get 6 state from 001 to 110 and for that condition we need to excite our 3-phase voltage source inverter module so that the stator of motor will get excited and it start run. So let me click on run button and will manually rotate and we will see the feedback first of all. Clicking on run button, here you can see that the condition first is 010, then by moving it, it will change the state 101. Here 011. Similarly we will get 6 states, so that based on this 6 state we need to excite our 3-phase voltage source inverter module. Then we will go with the digital output section. Here we are using 3-phase voltage source inverter module, so we require 6 digital output. Let me first configure this. From the waveform source I am going to take a square pulse. Here all the values are external control, so we require external value to configure it. I am going to take a constant block. Right click for the configuration window. Here 01 and for the switching frequency I am going for 20 kHz. Apply register. Back to schematic. Minimum 0 and the maximum 1 and our switching frequency 20 kHz. Here for the duty cycle I am going to take 1 hour. Just click on now, change the value. From minimum duty 0.1 to 0.8, apply register. Back to schematic. Click on this, connecting to the duty cycle by just connecting here. Here you can observe a square pulse. by click on trigger. Here by changing the duty, the pulse width is changing. The corresponding duty cycle of our semiconductor switches will be vary. Here this kind of motor we need to excite the gate signal based on the Hall feedback. Lookup table. Here the maximum digital input you can give D0 to D3, and this gate H and gate L will be top switch and bottom switch of each leg. It will be configured. Here we have 4 set of leg GAH and GAL and GBH. Since we are going only for 3 phase voltage source inverter module with a 3 leg configuration, so up to GCL we will configure. Just I am going to give the gate H and gate L same pulse, and the Hall feedback I am going to connect to the D0 first Hall, the second D1 and the third. 3 Hall feedback we have connected, and the gate signal. Now we are going to configure it. Based on the configuration, our gates will be turned on by right clicking on this block. We have the configuration window. Here we have 2 input, 3 input, like 4 input. If our inputs are 2 digital input or 3 digital input, either 4 digital input, mean we need to configure it based on that. Here for 0 condition, our all switches will be turned off. Similarly, like 1 condition, our switches will be turned off. First state is 100. For 100, we are going to excite AL and CH. AL and CH. Then for 010, I am going to configure AH and BL. AH, then BL. Then for 110, we are going to configure BL and CH. Then for 001, I am going to configure CL and BH. Then for 101, AL and BH. AL and BH. And final for 011, I am going to configure AH and CL. Totally 6 state. Based on this 6 state, each time we are exciting 2 phases, one for the top switch and one for the bottom switch of particular phases. Apply register value and back to schematic. Now we need to view the waveform. So let me take one logic analyzer. For 101, we are getting the output at second and third. Here second and third, GAL and GBH for 101. Let me have one clarification with connecting the LED for a Hall feedback signal. Now the state is 101. Here 101 we are going to excite AL and your BH. Let me check here. 101 we are going to excite AL and BH. Similar for other state it will come. By manually rotating, you can observe the change in the Hall feedback. So corresponding output will be enabled. Now it is around 1 and 4th pulse. This one first one, and then the 4th one it is connected. By simply rotating manually, we can observe the all feedback. Corresponding gate signal will be turned on, so the corresponding stator will be excited. Now we need to configure this digital output to the voltage source inverter module. Before that, we need a dead time for the top and bottom switch to overcome the shoot through. Let me take the dead time controller. Here configure the dead time controller like 1 microsecond, after register back to schematic. Now we are going to configure the digital output to the external connector, so that the voltage source inverter module will access that point. Let me take the digital output pin configuration. Here we have two set of digital output. One will be 0 to 5 volt level, so that we required one additional gate drive circuit, and we have another digital drive output with inbuilt gate drive circuit is been provided, so that it will gives the output level of 0 to 15 volt, not required of a gate drive circuit. You can directly connect your power semiconductor switches here, like your IGBTs and MOSFETs. Right click on the block for the pin configuration. From here it will configure to the direct power semiconductor switches. Here we are using the semiconductor switch as semicron module. After connecting it, I am here going to measure the current waveform. Let me take the analog input configuration block. Clicking on this, right click for the configuration window. Here I will connect the motor current waveform measurements. Here we need to configure the analog offset as well as gain value. Here we are going to use plus 20 and minus 20 pin configuration. Click on the for the value of your offset and typical. This value might be changes based on the signal respectively we are using. Here we are going with the default value. First 3 signal I am going to measure the bldc motor current waveform. I have assigned the gain value and the offset value we have assigned default values. Both are default. Values may be changes based on our signals. Let me view the waveform with the help of DSO. Click the output to corresponding DSO. Our first step, we have connected the motor feedback to the digital input area, and we are getting 3 digital input signal. From the digital signal, we are going to configure the gate drive circuits of your IGBTs. So for a particular state, we will excite only 2 switches, and each will be excited for 60 degree of interval. Per phase will be conducting for 120 degree. Since brushless DC are 3 phase sector, we will go for 120 mode. And here for the gate switching, we are simply giving the square pulse output with a variable duty cycle control, and we are directly connecting with the hardware power semiconductor switching modules. Let me now switch on the power supply. This bldc motor is a 24 volt. Just we have kept it a 20 volt DC bus link. Here you can observe the pulse width on time duty, it is in minimum now. By changing the duty cycle value, our output pulse width duty cycle will be changing, so the corresponding power semiconductor switch will be turned on for the particular duration and the motor starts exciting. Here you can observe, by changing the duty cycle, our DC bus current is increasing, so the coil is getting exciting. After getting the particular duty output, our motor starts rotate. Here you can observe here six square waveform output and your current waveforms of your bldc motor. This is a first phase and this is second phase and this is our third phase. Here you can observe your digital output from the all feedback. This is a first phase and this is second phase and this is our third phase. So first and the third phase are 120 shift and the second and third here it is 120 shift. You can clearly observe the motor feedback waveforms. So the corresponding phase we need to excite it based on these. By simply changing the duty cycle, speed of the motor is vary. One more thing, we will calculate the speed of motor by just using the speed to measure RPM block. Okay, pulse to PPR. Any one pulses we can connect it for the speed measurement. Right click on the block for the configuration window. Here the pulse per revolution will be 4 as per the motor data sheet. So apply register value and it will give the RPM calculation. Now for the RPM, let me take on display for viewing the value. Here you can observe that the motor RPM is currently 950 RPM. Totally we have done 3 module level design steps, one for digital input which we are getting from the motor feedback, your all sensor signal, and it gives in the digital output with a phase shift of 120 degree. Then we are going to excite our voltage source inverter module with this digital output configuration area, and for the current measurement I am going to use an analog area. Then for the speed measurement we are using this block. This is a simple open loop speed control of our brushless DC motor. We have done this experiment on real time configuration with our Snetly unit. In next video we will learn about the closed loop speed control of brushless DC motor with our Snetly hardware unit. Thanks for watching.